It's a privilege to open the session this morning, and I'd like to give you a wake-up call about what's going on in the cryosphere. My name is Mark DRINKWATER. I'm responsible for the scientific preparation of our Earth observation satellites, but my former career is in polar science. I've been working for two space agencies. I spent 15 years working for NASA before I joined ESA in 2000, and so I've had a combined career of around 30 years looking at the polar regions. And I'd like to explain how we use polar orbiting satellites to give us a unique perspective about the polar regions and what we call the cryosphere. The cryosphere is the frozen part of the Earth. This comprises ice caps, sea ice, the large ice sheets, glaciers, and permafrost or frozen ground. The cryosphere is a really important part of the climate system. It has a regulating impact on the energy balance of the Earth. It also interferes with the ocean circulation because of the way in which melt influences stratification in the ocean, has an influence on global ocean circulation. And it also influences society through the availability of water. And so I'd like to show some examples of how we're using polar orbiting satellites to give us an impression of how dramatic the changes are in the polar regions. It's quite astounding what we're seeing over the satellite record over the last 30 years. So if I can learn to change the slide. This is the only slide I show with words. It gives you a bit of a description of the types of impacts that we see in the cryosphere. So the cryosphere, as I said, all the frozen parts of the Earth. Polar air temperatures are observed to be increasing up to 4 times faster than the global average. This so-called polar amplification is having an impact on the consequence for melting of the ice and changes in the dynamics of the ice in the polar regions and in the cryosphere in general. We're seeing shrinking of the ice caps and the glaciers. We're seeing changes in marine ice. We're seeing permafrost thawing, which has an impact on infrastructure. We're seeing glacier retreat. And glacier retreat and shrinkage of ice masses worldwide is having an impact on water resources and the amount of water that's stored, particularly in the high mountain regions. And finally, we see the impact of changing ice and the cryosphere on ecosystems. It's changing habitats for species, and it's having an impact on the biology in the ocean, for instance. And as I said, much as in the atmosphere, the ice has an impact on stratification in the ocean. As fresh water enters the ocean, it changes the ocean dynamics. As a consequence, also has an impact on climate change. So the cryosphere has some really fundamental role. And what we'd like to do is to use our satellite capability to give us an impression of how it's changing. And in fact, what we see over the record is a quite dramatic picture. So we have polar orbiting satellites. This gives you an impression of how our satellites operate. This is one type of orbit which circulates in a way such that the satellite can observe the poles and observe the entire globe. We orbit close to the poles around 15 times a day. The orbit itself in respect to the sun is staying stationary, and the Earth is actually turning beneath the satellite. In this way, we build up stripes of data required by the instruments. You can see that they cross the poles on a frequent basis. This allows us to build up a picture over time using the repetitive measurements each time the satellite flies over the poles. This is the basis for the information that I'm going to talk about today. And it's the combination of satellites that we have today that give us this capability that I'm going to illustrate in some of the examples. So one of the systems that we've been developing, also in conjunction with EUMETSAT, is the Copernicus Sentinel series of satellites. Over the last 25 years, we've been building up a very comprehensive global observing capability together with the European Union and EUMETSAT, and a number of services that we'll hear about after my presentation. We have a series of 6 satellites that have been in development. Sentinels 1, 2, 3, and 6 have been providing data routinely now for a number of years, since 2014. They provide data 24/7 throughout the day. They're contributing, obviously, to our observations of the cryosphere. We're in the process of developing new expansion Sentinel missions. These are to fill gaps in our observing system capability, and these are complementing the existing 6 series of satellites. And we have three in particular that have been designed also to provide information about the polar regions. And you'll hear a little bit about these more in a moment. These are the Copernicus Imaging Microwave Radiometer, or CIMR, the Crystal satellite, which is an altimeter, and the Roselle satellite, which is a radar imager. These are all microwave satellites, microwave instruments, because the microwaves those instruments help us to watch the polar regions year round. Throughout the period of winter darkness, where we don't have sunlit region, optical instruments can only operate, of course, when we have sunlight. And so the advantage of radar in particular and microwaves is that we can observe year round throughout the polar night. So this gives us access to information about the poles 24/7. And with those data records, we're now constructing climate records. One of the most iconic changes in the polar regions are the sea ice decline. But the important climate record that we want to access is actually the volume of the ice in the Arctic and how that's changing year by year, season by season. Today, we're combining a combination of data products. Here you see in the top right how the sea ice is varying in extent and how it's varying in thickness. We have two types of measurements, one to measure the extent and one to measure the thickness with an altimeter, which shows the elevation of the surface of the ice above the ocean. That allows us to retrieve the thickness, and by combining the area with the thickness, we can access the volume. In the chart on the lower right, we can see how the ice grows in the winter and how it melts in the summer. So we have this pulse of sea ice extent and volume from one year to the next. And in building up this temporal series of data, we can give a climate record showing how the ice volume in the Arctic is varying from one year to the next. Now, today, we're combining Triosat and SMOS data to do this, but with the Copernicus satellite system and the combination of Sentinel-3, Crystal, and CIMR in the future, we'll be able to extend this record for decades to come, which is fundamental to the climate monitoring and understanding how the sea ice is varying from one year to the next. Now, if we turn our attention to the ice sheets now, we can also use our radar imaging capability to understand how the ice is changing. What we know from repetitive measurements is the dynamics of the ice sheet, and we can see how the ice sheet delivers snow and ice from the central part of the ice cap to the coast in ice streams. These are rivers of ice which carry the ice from the central part of the ice sheet to the coast. You can see the bright red tones around the periphery of Greenland, which illustrative of these regions where the ice is flowing most rapidly. Those ice streams discharge ice from the central part of the ice sheet to the coast, and where they start to float at the coast, we see icebergs breaking off and floating away in the fjord. Now, using the combination of Sentinel-1 satellites, A and B, with one satellite, we were able to acquire data every 12 days, but by having multiple satellites in orbit together, we can get far more frequent data. You can see that as we added the B satellite to the A satellite, we got more frequent data, but there's one very important characteristic that we're able to notice. You see the red dots in the lower chart indicate the velocity of the ice at different spots along the ice stream trajectory of the ice. And we can measure the speed of the ice and how it changes from one year to the next. And we can see now with the two satellites and the greater time resolution, we can see seasonal changes in the flow. So building up this picture, using this constellation of satellites, we can start to understand the dynamics of the flow and how that flow delivers ice from the ice sheet into the ocean and how that has a consequence for sea level rise. So if we build on that concept for a moment, we can now monitor all the drainage basins throughout the entire ice sheet using this fundamental monitoring capability that we have with Copernicus. We can watch every single glacier in Greenland, and we can add one of these little stripes for every single glacier by cumulatively adding up the ice loss from each glacier. There's no glacier that's gaining mass in net terms. It snows in winter, the ice builds up in the ice. But turn our attention to Antarctica. One of the things that we saw in the previous example from Greenland was this seasonal variation. What we see in marine terminating glaciers is that the ocean also influences the flow. How warm water is brought to the fringes of the large ice sheets is having an impact on the rate at which the ice flows. What we've been observing with the altimeters is that the surface is going down as the ice is flowing. So as we lose ice, the surface is deflating. We can also see that as the ice shelves, which is where the ice floats once the glacier reaches the coast, where the ice shelf is meeting that warm water, it's thinning. And as a consequence, we see the grounding line where the ice begins to float at the edge of the ice sheet. It's moving inland. Now, we treat West Antarctica as the, if you like, the soft underbelly of the ice sheet, because we see this sloping bedrock beneath the ice sheet. As the grounding line recedes, warm water can penetrate further and further inland, and this results in something we call marine ice sheet instability. And so West Antarctica is thought to be losing grip, and as a consequence of the interaction between warm water and the ice shelves fringing Antarctica, we're seeing changes in the dynamics, and we're seeing an acceleration of the ice loss because of global warming influencing the water temperatures as well as the atmospheric temperatures. So if we look at the right plot, we can see the places where that recession of the grounding line is most apparent, and we can see the arrows pointing inland, which shows the rate at which the grounding line is receding. That's worrying because we see the trend strongest in West Antarctica, where you see the warmer water in the red tones in close contact with the ice sheet. And so climate warming is not only about atmospheric temperature, it's also about the interaction between the ocean and the ice. So next example, if it can come up, let's see how many times I have to click here. Can you change to the next one manually, please? So we can add up now all of our knowledge of ice changes throughout the entire globe. We're monitoring all the ice caps, all the glaciers in the world using this wonderful Copernicus system. We can total up the amount of ice loss year by year in all the glaciers, all the ice caps, and in the large ice sheets. Now, in only 10 years, we've seen on average that the glaciers were losing about 270 gigatons of ice a year. We can total that up over a decade. And if you look at the plot, the wiggly plot with the red bars, you can see we can add up season by season, year by year, the total amount of ice lost from all of the glaciers. There we're talking about, over a 10-year interval, we're talking about 3,000 gigatons cumulatively over a 10-year period. Now, we can also add to that the amount of ice sheet, ice loss, from the examples I've shown you from Greenland and Antarctica. And there we're talking about another 11 or 12 gigatons of ice loss over the interval of time. And if we account for ice shelf melting and all the other sources of ice melt globally, we end up with a total around 28 trillion tons of ice loss over the satellite interval of measurement between about 1994 and 2017. And so this is a phenomenal capability that we have today to understand how climate is both impacting the ice sheets and the glaciers and the cryosphere, and the impact and the result which that's having on sea level rise. But first, to visualize this quantity that glaciologists love to talk about, gigatons, this billion tons of ice. We're talking about thousands of gigatons in the examples I've shown you. That's 1,000 gigatons is the trillion tons that I was talking about, and we were talking about 28 trillion tons. This is an illustration of 1 gigaton. Now, if you were to imagine the 28 gigatons lost over the globe in the interval of around 15 years, that would be the same as coating the United Kingdom with around 100 meters of water. That's just to give you a visual idea of what a gigaton or a trillion tons of ice might look like. This is an illustration of New York with an ice cube. That's one way of visualizing what a gigaton or a trillion tons of ice would in fact look like. Now, all of that water, of course, from the exchange between the ice sheets, glaciers, and the oceans, all that fresh water ends up in the ocean, and we'll see other examples from Pierre-Yves later from the Climate Service. But the most important message here is we've been in a very concerted way constructing a climate record from a series of satellites over decades now. Climate records require very careful calibration of the satellites, and we like to have this inter-satellite record that allows us to produce very accurate sea level change records, for instance. And we can plot the amount of sea level change, which is coming from eustatic sea level rise, which is the component of ice melt I just talked about. But there's another very important component, which is the fact that as the sea warms, we have thermal expansion, which is also contributing to sea level rise. And we can see about 45% comes from the ice, about 43% comes from thermal expansion, and there's around 12% from the other terms. We'll see more about sea level rise in just a moment, but over the satellite record, we can already observe around 8.5 centimeters of sea level rise. Much of that contributed from the warming of the ocean and the ice mass loss. So last one, I wanted to talk about water resource availability in high mountains and why cryosphere in high mountain regions is essential. It has very important socioeconomic consequences. But this is a result that's coming out in the press the last days. This is from the ICIMOC group, which is a UN organization which monitors the amount of snow and ice in the high mountain Asia region. We've seen extraordinarily low levels of snow accumulations this last year in the Hindu Kush and Himalaya. This has a consequence, of course, because the warming means that the persistence of snow in the mountains is not as great. With less persistent snow, the water is not stored in snow or ice in the mountains. And as a consequence, the runoff has a consequence for the people living downstream of those areas. And so with this regional warming, we see less persistent snow, and therefore we have less snow stored in these high mountain water towers. And we see downstream of Helmand, Tarim, Amu Darya river basins, we have around 30% less persistence this year. We have about 20% less in the Indus and Ganges river basins, and we have about 15% less in the Tibetan Plateau, the Yangtze, and the Brahmaputra. And of course, we're talking about 1.5 billion people who are dependent on this water that's stored in the form of snow and glaciers in the mountain regions. And so the high mountain part of the cryosphere is also a fundamental place that we have to monitor because of water resource availability. And so I'd like to conclude there. I think I've shown a variety of examples of how the cryosphere is changing and how dramatically we now understand it to be changing. This is a monitoring program that we absolutely have to continue, and Copernicus is really having a fundamental impact on how we're able to understand the dynamics and the changes of the cryosphere. And so thank you very much for your attention. Time for questions, I don't know. Should I stay here for questions?
Yes, we can ask. We have 3 minutes left. Are there questions? Maybe 1 or 2 questions? Yes?
Hi, could you repeat for me the comparison of the 100 meters of water on the UK? Was it for which period? Because I didn't.
Yeah, the satellite interval over which we've made this global estimate of ice mass loss was, I believe it was between 1994 and 2017. We've made an estimate of the total ice mass loss, which resulted in this 28 trillion tons of ice. Now, I was trying to make an analogy. If you were to melt that 28 trillion tons of ice, it would be equivalent to covering the United or the British Isles, if you like, with around 100 meters depth of water. That was the analog I was trying to provide.
So maybe 1 more question? No? Maybe from the community outside? No? Okay, good. Then thank you. Thank you, Mark. No. 1 more question. Yeah, please push the button there for the micro.
Oui, donc la comparaison avec
the comparison with the United Kingdom, that was for 1994 to 2017, but now things are going even faster. Do you have any prognosis estimations since 2017?
that was also too fast for me. Maybe
I try
can someone translate?
You said it was before between
94
and 2017, and from 2017. How much? Because it's accelerating.
Yes. So the fundamental thing is to calibrate these climate records in a very accurate way. And so the climate community has been working on the combination of all of these data over the most robust overlapping piece of time record that we have from the satellites, which runs from the beginning of our altimetry missions, which started in 1992, and until the present day. You're right, we observe the ice sheet decrease accelerating, but it takes quite some time to put some of these climate records together. Now, the most comprehensive assembly of these data is going on in the Copernicus Climate Change Service, and I'm sure we're going to hear a little bit more about that in a moment. But the science community likes to work on these data and make sure they have really robust results before they release the latest chapter in this series of results being updated. So I'm sure we'll hear more about the acceleration sea level rise. I showed a sea level rise number, which you'll see is slightly greater when you include the most recent part of the record. I think the most disturbing fact is that we do see an acceleration in sea level rise, which is in large part because of the accelerating ice mass loss. We'll see that in the sea level record, which Pierre-Yves is going to show in just a moment.
So, okay, thank you. We would like to continue. Thank you, Mark Drinkwater.